Hello, nice to see you again. Learning to interpret IR spectra can seem to require memorizing tables of numbers and functional groups like this. It's true that if you can remember all these numbers, then it would help, but I'm going to show you a much easier way. For this, it's necessary to know the high and low energy ends of an IR spectrum. Let's take a look first where the IR range is. It's here in the pink box, at shorter wavelength than the microwave region. That means it's at higher energy, because energy and wavelength are inversely related. We'll go over that in a second. IR waves are a longer wavelength than UV. UV is more energetic. We're going to look at the energetic origins of IR absorbances, how functional groups and a few bonds fit into this scheme, then try a few structural assignments. Intensities of IR absorbances are related to change of dipole as the bonds distort. Looking along alkene CC double bonds, the only dipoles are due to the substituents, so they give relatively weak absorbances. Carbonyl CO bonds have big dipole moments because of the electronegativity differences between the atoms. Carbonyls often stand out in the IR spectrum. Seeing one can give a big clue about what the molecule is. How about where certain bonds resonate in the IR spectrum? Think of two balls on a string. Pulling them apart and then letting them go will start a vibration. But what does the frequency of that vibration depend upon? For a given spring, bowling balls would vibrate more slowly than marbles. The mass of the two balls then makes a difference. For a given pair of balls, a stiff, heavy spring, like in a car suspension, would give a higher frequency vibration than a lighter one. It takes a lot more energy to stretch that stiff spring, and that's returned as a higher frequency, higher energy vibration when you let the balls go. Energy is proportional to frequency. They are related by Planck's constant. Wavelength times frequency equals the speed of light. So therefore, energy and frequency are inversely related to wavelength. Long wavelength waves, like radio waves, have less energy than shorter forms, like X-rays. In IR spectroscopy, absorbance on the y-axis is plotted relative to 1 over wavelength on the x-axis. Reciprocal wavelength is called wave number, and its units are centimeters to the -1. Get used to thinking about wave numbers because that's how organic chemists talk about IR vibrations. IR spectra are plotted from about 500 centimeters to the -1 on the right to 4,000 centimeters to the -1 on the left. The scale isn't linear, it's more condensed in the 2,000 to 4,000 region. Let's go back to balls on a spring. Springs are like bonds. Strong bonds give higher energy vibrations that occur at higher wave numbers. Connectivity between CC in alkynes is stronger than connectivity between CC bonds in alkanes because there are 3 bonds there relative to just 1. Sure enough, CC triple bonds stretch at higher wave numbers, that's higher energies, than CC single bonds, and alkenes are in between. Hydrogen bonded to carbon is lighter than carbon bonded to carbon is. It behaves like a lighter ball and vibrates with a higher frequency, higher wave number than a C-C single bond. Alkene CH bonds contain sp3 hybridized carbon atoms. Those are weaker than alkyne CH bonds, which have sp hybridized carbon. Electrons in sp hybridized orbitals are closer to the nuclei than in sp3 because they have more S content in the bond. CH bond energies in alkynes are therefore higher than in alkanes, even though they're more acidic. Terminal alkyne CH stretches then occur at higher wave numbers than alkane CH stretches. Let's look at some other IR trends. Along the series CO, CBr, Ci, the size of the ball, the atom, increases and the bond strength decreases. No surprise then, wave numbers for these stretches decrease along this series. Carbon monoxide has a triple bond. Carbonyls in organic compounds have only a CO double bond. So therefore CO stretches at a higher wave number because the spring, the bond, is stronger. It's good to remember a few numbers as mental anchors and then deduce approximate wavelengths for other stretches relative to these. One that I remember is 1715 centimeters to the -1 for the CO stretch of acetone, nail polish remover. Two dominant peaks in the spectrum of acetone are 1715 for the carbonyl and around about 2990 for the CH stretches. CH3 stretch wave numbers are worth remembering because nearly all organic compounds have them. This helps not misassign those peaks to something else and to calibrate sp3 carbon H and CsP2 carbon H, as I mentioned already. Where does the C double bond O stretch of acetone come relative to compounds with that carbonyl conjugated to something else? To think this through, consider this alpha-beta unsaturated ketone. Conjugation reduces the CO bond strength, and sure enough, it resonates at lower wave numbers. Similarly, for phenyl methyl ketone, the carbonyl is below 1700 centimeters to the -1. Oh look, we can see the CsP3 hydrogen stretch at around about 3000 centimeters to the -1, and the CsP2 hydrogens of the aromatic system above that. So this is the key for making interpretation of IR spectra fun. First, understand how wave numbers relate to atomic masses and bond strengths. Second, remember a few wave numbers for functional groups in certain compounds. And third, use ChatGPT to simulate IR spectra for you and then practice assigning peaks. All the IR spectra in this video are simulated by ChatGPT. Here is a simulated spectrum of ethyl acetate. There is the ester carbonyl stretch. These are the CsP3 hydrogen stretches. And I'm going to estimate that this one down here is the CO single bond stretch. Isn't this fun? I have combined this video and some others into an animated workbook of problems for mastering Introductory Organic Chemistry. That ebook is available on Apple Books, Kindle, and Vital Source. Thank you for watching. And thank you to the folks at the Engine Room in Southport, UK, for allowing me to use their studio. Bye-bye.